Hello, statisticians. Mr. Youngsaver here from Skew the Script. Today's lesson is to take you back to November 8th, 2016, when Trump pulled off a shocking upset, beating Hillary Clinton against all the polls in the general election for president. We're going to look at what happened with those polls, why they were so far off, and what that shows us about potential problems for confidence intervals and hypothesis tests when using statistical inference. Let's skew it. Today's lesson is on problems with intervals and tests. This is lesson 7.6 in our course sequence. I want to first take you back to November 7th, 2016, the day before the election that year. Multiple news outlets were reporting that Clinton was a heavy favorite. The Huffington Post in their forecast said she had a 98% chance of winning. The New York Times said she had a 90% chance of winning, and Trump's chances were slim to almost none in some cases. And then November 8th, when everyone went to the polls, everyone was expecting a blue outcome. The Democrat, Hillary Clinton, would win the election, and then suddenly red. We saw that Trump was winning states that Republicans hadn't won in years, and he won the Electoral College, winning the overall election. Now, Hillary Clinton didn't win the popular vote, but Trump won the game at hand, which was the Electoral College. In particular, one of the biggest surprises was Wisconsin and Michigan. Wisconsin and Michigan have been blue, voting for the Democrat ever since 1992. Every single general election since then, they've voted for the Democratic candidate. But in 2016, they went for Trump, the Republican candidate. And this was not only shocking because of history, but also because of the polls leading up to that election. In Wisconsin, they did many, many polls of the population, and they saw for each time Clinton was up by a certain amount of points. This was in June 2016, in August 2016, and all the way through October 2016, you see Clinton, every single poll was up. But then on election day in November that fall, Trump won the vote in Wisconsin. So today's key analysis will be, did Trump get lucky and by chance alone happen to get more votes than what the polls would show, or were the polls just plain wrong? If you want to follow along using guided notes, you can go to this URL here to print up that handout. So first we're going to talk about the ideas of bias and error and how they're different. Bias is when our estimates tend to systematically under or overestimate a population's parameter value. An error, by contrast, is when an unbiased estimator produces an estimate that slightly misses his mark due to some chance variation in the sampling process. So going back to that election, Trump versus Clinton, among Wisconsin voters planning to vote for one of these two major party candidates, what proportion of them will vote for Trump? That was a question a lot of pollsters were asking. And let's pretend, we're going to theory land again, pretend we knew the population proportion. We knew that among major candidate party voters, 60% of them in Wisconsin are going to vote for Trump. Let's imagine we knew that. Of course, we don't know that because we are unable to measure everyone's ideas and what they're going to vote for before election day, but let's imagine we did. And so we're going to go to more of the human realm, the realm of statistics, because we can't measure everyone in the population, and get some samples, some random samples to try and estimate that proportion. So let's say we get a sample of 30 people, 17 out of 30 will vote for Trump in that sample as they report to the pollster. That means 57% is our estimate for the proportion of voting for Trump. We underestimate the proportion of voting for Trump in that case. But what about the other possible random samples that could have happened from that population but didn't? Let's talk about this possibility. Here's another random sample that could have happened. In this case, 19 out of the 30 we happen to select for Trump voters. That's 63%. We overestimate slightly. Here's another possibility in which 18 out of 30 vote for Trump in our poll, and then we match it right on. So there's some random chance here in our sampling process. Now, we know from our previous work with sampling distributions what happens. The first possibility, we underestimated slightly. The second one, we overestimated with our sample. The third one, we were right on. And if we do this many times, over and over and over again, if we do it among all possible random samples of size 30 from that population in Wisconsin, we should get a sampling distribution centered at 60% voting for Trump, with some variation due to chance above and below. This is an unbiased sampling method. It doesn't tend to systematically over or underestimate the true parameter value. It's centered at that value. And sometimes, say we did one random sample, by chance, we might randomly sample fewer Trump voters than expected in our sample. This produces an error. In this case, we underestimate. But what we can do is make a little confidence interval around that estimate that with its margins of error should capture the proportion at a certain level of confidence. This is why we give intervals margins of error because we know there's some natural chance variation error that comes with every estimate. For unbiased errors, we still expect errors. For unbiased estimators, excuse me, we still expect errors because of chance variation in the fact that we're randomly sampling and might happen to get more Trump voters or less Trump voters than expected. So if the underestimates in the polls were underestimates by chance alone because of these sampling errors, we should see the polls look like this. Some will overestimate, some will underestimate, and in the confidence intervals, most of the time it should capture the true proportion voting for Trump. The polls would center at that true proportion with some errors on both sides due to chance variation and sampling. And most would capture that proportion in their margin of error if they're using big enough margins of error. But that's not what we saw in the Wisconsin polls. This is what we saw instead. We saw every poll systematically saying Clinton had a pretty big margin of lead. And on the actual election day, that just wasn't the case. What we actually saw was confidence intervals that looked like this. And so we know the polls were biased because systematically they were underestimating Trump's chances. What happened that made the Wisconsin polls biased? Well, there's a couple of reasons that a lot of people have come up with, including Nate Cohen, as well as Nate Silver, famous statisticians who do poll work. There was non-response bias. Less educated people tend to be less responsive to polls when people survey them. And usually this isn't a big problem in elections since less educated people tend to split their votes between the major party candidates. But this time, in the 2016 election, they voted heavily towards Trump. A lot of polls, especially state level polls in Wisconsin, didn't adjust for this and they underestimated Trump's vote totals. The effect was especially big in Wisconsin since that state has many white voters that don't have college degrees. There was also undercoverage bias. Polls cannot figure out how undecided voters will cast their ballots when they step into the polling booth. If you interview a person a day before the election, you don't necessarily know if they're undecided how they're going to vote on election day. Usually this isn't a huge problem though because undecided voters will tend to split their votes between candidates, but some results after elections suggest that undecided voters broke towards Trump when they, especially in Wisconsin, when they stepped in the voting booth. So these votes were undercovered by polls more so than usual. There's other potential biases, but these ones don't have as much evidence towards them, but people have posited these might have happened to make the bias happen. So why do we always have to check these conditions that we're talking about inference? Well, this is why. This is the exact reason. Making estimates or intervals or hypothesis tests using bias estimates is completely meaningless because we're not being accurate. Our inference methods account for error. That's why we have margins of error. That's random sampling error. But they don't account for bias, which is systematically under or overestimating. The random condition, making sure we have a random sample from the full target population, not just an undercovered part, is one way to make sure we check for bias. So now, talking about error and not bias, let's talk about type 1 and type 2 errors. So say it's November 8, 2016, voting just closed in Wisconsin. So votes have already been cast. And you want to quickly estimate the proportion of voters who vote for Clinton. You don't have time to count all the votes. You're going to take a sample. You get a simple random sample of 500 votes from all Wisconsin ballot boxes. According to many election experts, candidates that get 47% or more of the vote tend to win elections. About 3% of the votes usually go to third-party candidates or people who write in stuff like Mickey Mouse or something silly. Now, of the 500 sample votes, 255 that you got in your sample were for Clinton. Use a hypothesis test to determine if there's convincing evidence that Clinton will win the election in Wisconsin. In this case, there's no reason to expect bias because we're randomly sampling from votes that have already been cast. We're not really undercovering, we're doing a true random sample process. So there may be error though still because we're doing random sample from a larger population. So we'll see if that error comes into play here. So we set a cutoff at 47%. That's what you need to win. So we're going to say that the null hypothesis is that she earned 47% of the votes. And the alternative is that she earned more than that, enough to win the election, where P is the true proportion of voters who voted for Clinton. So we can build a sampling distribution around that null hypothesis saying, okay, assuming the null is true, we say these are the sample proportions we could get if exactly 47% of people voted for her. And these are all for a sample size of 500. And we set an alpha level of 0.05. We're only going to reject a p-value if it's 0.05 or less. And that rejection region is right here in our sampling distribution. If we get a sample portion above that region, the p-value will come out to less than 5%. But what that means is if the null hypothesis is true, by chance alone, we might overestimate the proportion of people voting for Clinton because we got an unusual sample that got more Clinton voters than expected. So 5% of the time, that's going to happen, given the probabilities we have here. Now, our sample proportion was 255 out of 500, which is 51%, which is right there. It's in our rejection region. We would reject that because it would have a low enough p-value to reject. So should we actually reject the null hypothesis? and conclude Clinton will win Wisconsin given our sample? Or did we just happen to, by chance alone in our sample, get an overestimate of Clinton supportive of votes because of the chance process? This is what we consider a type 1 error. If the Clinton voter rate is truly 47%, the null hypothesis, the probability of getting a sample proportion of 51.51 or less is less than 5%, excuse me. So we reject the null, but she didn't win Wisconsin. So this would have been a type 1 error. By chance, the 500 people we randomly sampled happened to be more supportive of Clinton than the general population. So we falsely rejected the null because of that unusually Clinton supportive sample we got by chance alone. This isn't bias, this is error. That is called a type 1 error, when you reject the null hypothesis, but the null was actually true. And type 1 errors happen alpha percent of the time. Wherever you set your alpha at for cutoff of p-values, that's the rate at which you will make type 1 errors. So let's assume the null is true, exactly 47% vote for Clinton. We got our sample proportion. By chance, unusual samples will happen alpha percent of the time. In this case, 5% of the time we'll falsely reject. Now, if you want to make sure you get less type 1 errors or less frequent type 1 errors, you're going to make your rejection region smaller by making your alpha level smaller. That's going to make it harder to reject the null hypothesis because you need a smaller p-value. You need more unusual data to reject the null, but it's going to make sure that you prevent type 1 errors that make them happen at a lower rate. Now, the type 2 error is the converse of this. When you fail to reject the null hypothesis, but the null is actually false. In other words, you should have rejected it, but didn't. And if you want a little chart to show you what type 1 and type 2 errors mean, here's a really handy one right here. So now let's talk about a problem that compounds these kinds of errors called the problem of multiple tests. Imagine you really want Clinton to win Wisconsin. So you take a random sample of 500 ballots and find that 230 voted for Clinton. That's only 46%. So that's not enough to really prove that she's going to win. But you know that Wisconsin usually votes blue. So you think, oh, this must have been an unusually small sample for Clinton. So you take another random sample of size 500 thinking that one must have been unusual. And in this one, 215 voted. That's even smaller. What? Something weird is happening. Okay, I'm going to take another one. And you keep on taking random samples until you finally get one where, say, 257 voted for Clinton out of 500. 51.4%. That's enough to conclude there's statistically significant evidence for Clinton to win. She's going to win. What's the problem here? There's a real problem here. And that's this. Alpha is 0.05%, or sorry, 5%. That means you have a 5% of getting an unusual sample that will reject the null hypothesis, even if it's true. So say that you get sample 1, which was right here. And you're like, okay, we're going to throw that one away. You get sample 2, it's right there. Okay, we're going to throw that one away. Sample 3, it's right there. Well, we're going to throw that one away. Keep on throwing away and sample, sample, sample until you finally get one that proves the claim or shows evidence for the claim you want to show. Say, aha, we can reject the null hypothesis. This is too unusual for the null hypothesis to be true. When you run a test and sample many times, you might be doing what's called p-hacking. You're fishing for a sample, a random sample, that will prove your point, even though all you're doing is trying to find a sample that's unusual enough to make a type 1 error. So you shouldn't run multiple tests like this because it really increases your chance of making a type 1 error. If alpha equals 0.05, then 5% of the time you're going to do a type 1 error. You're going to reject the null by chance alone. So this means 1 out of 20 times it's going to happen. 1 out of 20 samples. You're going to get an unusual sample that rejects the null. So if you take samples over and over again, you're basically adding on to that probability, and eventually you're bound to get a sample you reject the null even if it was true. This is called the problem of multiple tests. So you should avoid this, and here's a way to avoid it. Get one sample, the highest sample size you can muster, and whatever results from that sample are your final results. Just take it as is. Don't do it again. Don't repeat a test or do many very similar tests, but if you need to repeat a test, you should lower your alpha level to make that rejection or type 1 error rate smaller. Now, let's talk about power. Power is the probability of correctly rejecting the null when it's actually false. And the effect size has to do with power. It's the difference between a proposed null hypothesis value and the actual parameter value. Let's talk about what I mean here. Power is the opposite of the type 2 error rate. It's the probability of correctly rejecting the null when it's false, whereas type 2 error is the probability of failing to reject it when it was false. So you can just do 1 minus power is the type 2 error rate. Usually, you want a test to have a high power. So you know that if the null is actually not true, you have a good chance of correctly rejecting. You want a high chance of doing that. It's a high power. Now note, the AP exam really tests your ability to do exact power calculations, but it does test your intuition about what power is and what it's affected by. So we're going to talk about that here. We're going to talk about a new example. Say there's a research team testing the effectiveness of a new systolic blood pressure drug, drug B. And the doctors in the research team say that if you can lower systolic blood pressure by 10 points or more, such a difference will have meaningful health benefits. So if you lower blood pressure by fewer than 10 points, it's not really a medically meaningful difference. So blood pressure changes are distributed normally and have a standard deviation of 21.5 points between people. You give the drug to a group of 20 subjects, randomly assigned the order to get the drug in. What is your power to detect a true average blood pressure drop by 10 points at this sample size? So here are my hypotheses that the default is this drug is ineffective. It's not going to lower the average blood pressure. The alternative is that, yes, it does. It's effective. It's going to lower the average blood pressure. We're going to see if there's convincing evidence of that from our sample. So here's the null, here's the alternative. This is the effect size we're hoping to see, that 10 points or more drop in blood pressure will be medically meaningful. So that's the effect size. So now we're going to go through the test. We're going to assume the null hypothesis is true, that this drug is not effective. So that means that any sample mean with a blood pressure drop greater in magnitude than 7.88, given that we've chosen alpha level 0.05, will result in correctly rejecting the null hypothesis. So if the effect size is actually 10 points, if the drug drops systolic blood pressure by exactly 10 points on average, let's see how often we would correctly reject that null hypothesis. So in this rejection zone, we're going to make the sampling distribution in the alternative case, in the case where it is true that this drug is effective by a magnitude of 10 points. And in this case, we would get sample means 67% of the time that will correctly result in rejecting the null. The power of this test to detect a 10-point drop in blood pressure to reject the null hypothesis is 67%. That's the percent of the time we will reject it. So if the true effect size is a 10-point drop in blood pressure, we'll correctly reject the null 67% of the time. But this is pretty low. You might want more power. You might want more higher probability of rejecting the null, proving your drug is real and effective. So what can we do? Well, there's one method. You can increase your alpha. So when you increase your alpha, the rejection region becomes higher because you're getting a higher probability there. And then that will increase the power automatically because you're kind of having a different standard of rejection. But recall that alpha is the type 1 error rate. So even though increasing alpha will increase your power, it also increases your chance at a type 1 error. So don't increase the alpha. That's just kind of like cheating. It's increasing your type 1 error rate. Don't do it. Now, another way to do it is to raise the effect size. So say the drug was even more effective. Say it didn't just lower blood pressure by 10 points, it lowered it by 13. What happens then is the sampling distribution for that shifts over. And so more of the time, we're going to see sample means that are going to show that we've rejected the null because the drug was even more effective than we anticipated. However, this is impossible to affect the effect size without actually changing the drug itself. So it's not something statistically that we can do because this has to do with the drug, right? So the best way, usually as a statistician, we can do to raise the power is to raise the sample size. Remember, raising the sample size makes your estimates more precise. These sampling distributions are going to shrink and become more narrow. And when that happens, you're going to get more precise means around that effect size of -10 and reject more often. So usually raising the sample size is the best way to increase your power. And this should make intuitive sense. Here's why. If a drug is effective with only 3 people, you may not be convinced it works with everyone because you're only sampling 3 people. It's a low sample size. But if you show the drug is effective with 10,000 people, you'll be more sure it's generally effective for the general population because you have a lot of convincing evidence there. So if the drug is effective, increasing the sample size will make you more likely to detect that effectiveness because you're going to see it in more people and your estimates are going to be more precise. You're more confident in them. So there are 3 ways to recap to increase power. Increase the alpha level. Don't do that. It's cheating most of the time. Increase the effect size. Don't do that. It's impossible most of the time. Increase the sample size. That's usually a good way to do it. So let's have one quick discussion question I'm going to leave you with for today. This is one of my favorite cartoons in statistics from XKCD. I want you to take a moment, pause the video, read through it, and your discussion question is, what statistical problem is this cartoon pointing out? How might this problem be an issue for scientists testing new ideas, medicines, or theories? That's it for today's statisticians. Have a good one.